And next up, we have Matei, who's going to tell us about Mesos, which is the underlying cluster scheduler that's actually running the whole demo right now.
Okay, hi. Thanks, Michael. So yeah, my name is Matei, and I'm working on Mesos with a bunch of people. Ben Heinemann and Andy Konwinski are their grad students. Ali Gadzi is a postdoc, and we also have Anthony Joseph, Randy, Scott, and Jan. And Mesos is the cluster scheduling system that we've built in the AMP lab and that we're continuing, that we've built in the RAD lab and that we're continuing to work on in the AMP lab. So the RAD Lab has actually looked at cluster scheduling for a while, and you've heard all about the scheduling for storage and web applications. I'm also going to talk a bit about what we did for analytics. And starting in fall 2007, actually, we saw this platform called Hadoop that was popping up everywhere and becoming very popular, and we decided to try it out and to look at some of the issues involved with that. And we've actually had a bunch of projects on Hadoop and Dryad scheduling in the lab that have led to code that is now running in production in Hadoop and in Dryad in multiple companies. So here's just a list of some of the projects. I'm not going to talk about all of them, and maybe I've missed some as well, but this is just gives you an idea of some of the things that we've done in this space. What I am going to talk about now is Mesos, which is, in a way, it's a logical extension of some of this work. So even though we started by looking at job scheduling within, say, a Hadoop data warehouse, real data centers are running much more than just MapReduce. They're running a very diverse mix of applications. And in fact, this is true both even on the analytics side. There are more frameworks than just MapReduce that people want to use for parallel processing. So just some of the things that motivated Mesos are the new programming models that are arising. So just in the past year or 2 years, Google has talked about something like 3 or 4 programming models that complement MapReduce. They include Pagel, which is for graph processing, Dremel, which is for low latency analytics on column-oriented data, and their new indexing system called Caffeine, which is an incremental computation system. And of course, you'd like all of these to be able to share resources efficiently. And storage systems, again, you have a variety of systems with different trade-offs in the properties they provide. And of course, you have your web applications. So we would like, basically, we would like a resource management solution that can efficiently share resources across all of these applications. And of course, not just across present applications, but across the future programming models and storage systems and so on that will keep arising in this space. So I'm going to talk a little bit about the goals and architecture of Mesos and then show you some experimental results we have with the system. After I do that, I'll also spend a couple of slides talking about one particular policy we've come up with for resource allocation in data centers that we think is very interesting. It's an extension of weighted fair sharing for multiple resources. So when you have, say, both CPU, memory, and network bandwidth, how do you do weighted fair sharing among applications? And this is work that's come out of seeing this problem in Mesos. And finally, I'll conclude with a summary of where Mesos is today. So let's take a look a little bit at Mesos. So Mesos is this layer, this infrastructure layer that runs on your nodes that these diverse applications can talk to in order to acquire resources on the cluster. And basically, the main goal of Mesos is to give these applications an API that allows them to efficiently share the cluster. And what we mean by that is that they should be able to achieve their own placement goals that they might have. For example, data locality for MapReduce, and at the same time, the system as a whole should achieve high utilization, low latency for new jobs, and of course, scalability, and so on. So this is a very high-level picture of the system. Now, for the actual system, we had a number of goals, and because this is generally a very hard problem to do cluster scheduling for a wide range of applications with different requirements, we wanted to focus on some particular goals with Mesos and explore this design space. So one of the goals we had was scalability. We wanted a system that you could scale up to manage tens of thousands of nodes, and the reason for that is the more nodes you manage, the more statistical multiplexing you can achieve. And everyone in industry that we talked to wanted more and more nodes per unit that they schedule. We also wanted the system to be robust, which means both to sort of bugs, or to limit the complexity of the system, but also to be robust to node failures and especially failure of the master. Because if this resource scheduling system goes down, all the applications in the data center that depend on it can't acquire new resources anymore. And the last thing is that we wanted the flexibility in terms of the types of applications we support. And we wanted to support both the current parallel processing frameworks and future applications, which might have very diverse resource requirements. So again, as I said, there's a wide design space here that trades off between these things. So if you know your workload very closely, you can build maybe a centralized scheduler that optimizes things very well for that workload. What we wanted to do is sort of at the opposite end, where you have the diverse set of applications maybe written by different people, and you want them to still coexist nicely. And the design we came up with is a very minimal microkernel-like system where applications control their own scheduling, and Mesos sort of mediates the scheduling and enforces some inter-application scheduling goals that you might have. So I'll talk more about what that means. So in particular, there's two pieces to the Mesos design that we see as two of the contributions. One of them is the fine-grained sharing model. What we mean by that is that we're sharing resources not at the level of physical nodes or VMs that you statically partition and that last throughout the job, but rather at the level of smaller tasks that are units of work within your application. So for example, in a MapReduce system, these are your map and reduce tasks. And this is different from a lot of the scheduling systems out there today, things like virtual machine clouds and HPC schedulers, which all do coarser-grained sharing. And having this fine-grained sharing lets you get higher utilization, lets you change allocations more quickly, and also lets you achieve goals like data locality more easily. The other element that we have is our scheduling mechanism called resource offers that allows applications to make their own scheduling decisions. And we'll talk about how that works next. So here's a picture of Mesos and with two applications running on it, just so we can see all the components in the system. So we see there's a Mesos master node and a number of slaves. And then each application has two pieces. So one piece is the scheduler. This is a component that talks to the Mesos master and figures out what resources it wants to use and when to launch tasks and what to do as they finish. So this makes the scheduling decisions for the application. And the other one is the executor. In this case, there's only MPI executors, which actually runs the tasks. There's just a binary you provide that runs the tasks. Okay, so here's how resource allocation works in the system. So first of all, the Mesos master will always monitor the resources on the slave and will know when there are not some resources that aren't allocated. And when it finds these free resources, it decides who to make a resource offer to based on an inter-application sharing policy. So this could be something like priority. You might say Hadoop should always have priority over MPI. Or it might be something like weighted fair sharing, where you say, well, Hadoop should get 20% of the cluster. So this is an organizational policy between applications. Once this happens, the master puts together a resource offer, which is a description of the available resources. So let's zoom in on that. Each resource offer is a list of pairs where you have a machine and a vector of resources that are available to be allocated on that machine. So here we have two nodes and maybe different amounts of resources on each node. And this resource offer is then sent to the application that we chose according to our policy. And here, for example, say that we chose it to Hadoop. Now, the application scheduler does the inter-application scheduling of deciding which nodes it can use. So, for example, which nodes does the MapReduce job have data on, and also which tasks to launch on them. So in this case, maybe we have data on slave number 2, but not on slave number 1. And then the scheduler responds to the offer with one or more tasks to launch, and these pass to the master and make their way to the slave. And then the slave is responsible for launching the executor, monitoring it, and also isolating different applications. We use OS technologies like Linux containers to isolate these applications. So that's how resource allocation works. And some of the nice things about this model are that the applications themselves can have their own logic without knowing about each other. They can have their own logic for placement, for dealing with failures, and so on. And the Mesos master, because it only does inter-application scheduling, is highly scalable and also easy to make robust, as I'll talk about soon. Okay. So that's, oh yeah, and now last thing I always forget to mention is now there are still some free resources in the system, and you can actually you can now offer these to a different application because Hadoop didn't want them. So we might offer these to MPI next. Okay. So I'm going to present now some results showing different aspects of the system. And these are actually from an upcoming NSDI paper that we have on Mesos, where we ran many experiments on Amazon EC2 to test out the system. So the first one I'll talk about is just a macro benchmark where we put together 4 applications, pretty different applications, and had them sharing resources and compared this sharing at a fine granularity on Mesos with static partitioning that you do with many of today's cluster schedulers. So we had 4 applications here. Spark is a iterative in-memory MapReduce system that we've built directly on top of Mesos to handle some of the applications that Hadoop itself couldn't handle well. We have 2 instances of Hadoop. One is running some large batch jobs, and one is running a mix of small and large jobs based on the Facebook workload. And then finally, we had MPI, and we actually ported the Torque cluster manager to run on top of Mesos and dynamically scale up and down and run MPI jobs. So each of these were submitting different jobs at different times, according to some schedule that we had. And the main thing to notice here is the different applications have peaks in demand at different times. So for example, this red one, the large Hadoop job, at this time, it wants to run a job, and gray Spark doesn't want to run a job, and the Torque and Facebook Hadoop are below their share. So it can actually scale up dynamically and use more resources than just a quarter of the cluster, which is the fair share that we wanted this application to have. And as you go along, a lot of the time you can keep all the resources utilized. Of course, there are also times when the overall demand is too small. But you can get pretty high utilization, and you can reallocate resources very quickly when demands change. These ramping up and down happens on the order of seconds. Okay, this slide here compares the shares of the applications on Mesos with what you'd get with static partitioning. So if we just gave a quarter of the cluster to each of the applications, and the blue shaded things are showing static partitioning, and the black lines are Mesos. So I hope you can see this, but basically the main thing we notice here is that on top of Mesos, the applications can sometimes scale up below their fair share, and as a result, jobs finish faster. So in particular, the large Hadoop mix is the most obvious one. It often gets to scale up, and these 10 jobs that it's running finish in about half the time in the shared system. And this is exactly what we want to enable. But the other ones have similar properties where they can scale up opportunistically and grab more resources. Okay, so that's showing that you can do dynamic resource sharing. Now, we also want to meet applications' scheduling goals, and that's what this experiment is about. This experiment is evaluating resource offers, especially as a means to achieve data locality. So in this experiment, we had 16 instances of Hadoop MapReduce running on 100 nodes, and they were all running large jobs. And we wanted to see what data locality they get with static partitioning of the cluster versus resource offers and fine-grained sharing using Mesos. So we have four scenarios we compared here. So in the first one on the left, we just split the cluster into 16 equal pieces and run each Hadoop job in it. And here you get very poor data locality because the data we had was actually on a distributed file system that was shared by all the nodes. So this is, so your 1/16 of the cluster doesn't have most of your data blocks on it. And this is exactly, part of the reason why people have moved away from Torque and HPC type of schedulers for Hadoop, and they've done fine-grained sharing inside it. Okay. The next graph here shows if these applications just running on Mesos but not doing anything smart with the resource offers they get, just accepting every offer they get when they have a task. And using this, you get higher data locality just because we share each node among multiple instances of Hadoop. And actually, in the graph at the bottom, you see this translates to a lower running time as well. But it's still only 50% locality, which is not great. And then the two graphs over here show what happens when the applications implement delay scheduling, which is a policy we initially developed for scheduling within Hadoop that lets you, where you just wait a small amount of time for a resource offer that has local data for your application. So even if you wait only 1 second to get one of these offers with local data, you can get to 90% data locality, and you can get to significantly lower running time, almost a factor of 2 lower running time. The one interesting thing about this is we had done this algorithm inside Hadoop anyway. So, and in fact, most of the scheduling algorithms in Hadoop are online algorithms like this. So it's very easy to run this on top of Mesos with resource offers. Your Hadoop code is set up for online scheduling anyway. Okay. So that's the actual scheduling, and the other pieces that I'm going to talk about now are scalability and fault tolerance, because these are also important goals of the system. So this next slide shows a scaling up test that we did again on EC2. And the main thing that makes it easy to scale Mesos is that we only make these inter-application scheduling decisions. So things like fair sharing or priority. So we don't have to know about all the tasks you have pending, all the dependencies you have between them. We just have to know that, we should offer resources to Hadoop before we offer them to MPI. And that makes the Mesos master code very simple and very, very streamlined. This is usually quite a bit faster than the intra-application scheduling that individual frameworks will do. So in this graph, we launched 200 EC2 nodes, and we ran up to 50,000 Mesos slave daemons on them, and 200 applications. We had, I think, 2 tasks per node. They were 30-second tasks, so there were 100,000 active tasks, and there were 33,000, I guess, scheduling decisions per second. So this is a pretty high load, higher than I think in most of the Hadoop clusters that are out there today. And the graph here shows the extra latency from launching a task through Mesos as opposed to just running it on a machine. So what we did once this workload was running on the 50,000 nodes, we ran one more application that launched one task. And we measured how long it takes for the resource offer to make its way to the application, to get accepted, and then for a status update to come back when the task finishes. And what we see is that the latency is always below 1 second, which is really nice because these tasks are usually at least a few seconds long. Okay. So that's scalability. And then the other place where the Mesos design helps is with fault tolerance. So again, the Mesos master has only this very limited job of implementing the inter-application scheduling policy. So the state it needs to know is actually all soft state. It just needs to know the list of active applications and the list of running tasks on the cluster. It doesn't need to know anything about the submitted jobs that you want to run in the future. And because of this, if the master goes down, we can actually launch a backup master and recover the state just by having all the applications and slaves reconnect to us. So that's what we tested in this graph here, which is up to 4,000 slaves. We looked at the recovery time for launching a new master. And to actually do the leader election and detect that the primary is down, we use Apache Zookeeper to do this. So again, recovery time's pretty small just because we only wait a bit for these guys to reconnect to us. Okay. So that's it for the experimental results. And so, these basically what these results have validated for us is that this is maybe an interesting point in the design space, and we want to see how far this model extends, this decentralized scheduling model. Because if it does let you get very close performance to an optimal scheduler, then it's very attractive to stay in this model because it's so easy to scale up and to get fault tolerance. Okay. Last thing I'm going to talk about is a policy we came up with in the Mesos project for fair sharing. It's called dominant resource fairness. And this just came out of thinking about this problem a little more in the context of Mesos. So one of the most common resource allocation policies especially for analytics systems like Hadoop and RAD is weighted fair sharing. And it's because it's easy to understand for the users, and it's also easy for administrators to set policies. Like, you have 2 times a higher share of the cluster than I do. But usually fair sharing has only been defined in terms of one resource type. So in Hadoop, there are slots, for example, where each task is assumed to consume the same amount of resources, and there's a similar concept in Dryad. In Mesos, however, we allow tasks to have different quantities of different resources. And the natural question is, how do we get a policy like fair sharing when you have multiple resource types? So for example, if my job needs a lot of memory per task and your job needs a lot of CPUs per task, how many tasks should I get? How many should you get? That's the question. So we looked at several properties of fair sharing that makes it attractive, and we tried to come up with a policy that maintains these properties for multiple resources. And I'm just going to list 3 of them here. So first on sharing incentive, this just means that if I have, say, 100 nodes and you have 100 nodes, and we put our nodes together, we should each be better off in the shared cluster than we are with our separate allocations. And it turns out actually that some of the simplest policies for fair sharing, like just assigning a cost to each resource and equalizing those values of your tasks, don't actually have this property. So we had to do something fancier to actually get this property. Another important one is very, very basic, is envy freeness. If we have equal shares, I shouldn't prefer someone else's allocation to mine. So that's, you want to preserve that. And the last one that's really interesting is strategy proofness. So we found in talking to you guys that users in real clusters are very clever about getting the most resources they possibly can out of the system. So for example, we heard about MapReduce users who saw there were a lot of reduce slots free, not many map slots free. So they wrote their job to use only reduce tasks, and they forfeit all the data locality of MapReduce. They create a lot of traffic, but they got their job done faster that way. We've also heard from another company about users that were told you can't have a dedicated machine unless you have higher utilization than some threshold, so they just added some busy loops in their code to reach that utilization. So users are very creative, and we wanted a system where you're incentivized to report your demands accurately and to not cheat to get a higher share of the system. And I don't have a lot of time to talk about DRF here, but this is another paper that we have at NSDI in April. And the idea in DRF is actually pretty simple. Is we look at which resource you need the most of as a fraction, and we equalize people's shares of that. But it turns out that this has these properties, and that it's actually better than, in terms of these properties, even than one of the leading solutions in microeconomic theory, which is competitive equilibrium from equal incomes. The other thing that we believe is that actually DRF is the only allocation scheme that has both the sharing incentive and strategy proofness. And there's an economist at Berkeley, Eric Friedman, who's working on this. So I think he's proved that for 2 and 3 users, and now he's generalizing beyond that. So that would be a really interesting result to have. So that's DRF, just to give you a taste of it. So in conclusion, we're really excited about pushing Mesos forward into the AMP lab. The system already supports a variety of applications, including Hadoop, SCADs, Rails, and MPI. And we're also using it to build new frameworks such as Spark, which Justin is going to talk about next. We're also deploying Mesos and actually eating our own dog food and trying to get other people to eat it too. So we're using it in Berkeley to manage our cluster in the lab. We also have Ben Heinemann working with Twitter, and they're actually running production services on Mesos on more than 100 nodes right now. And finally, we've open sourced the system under the Apache incubator, and we invite you to check it out online. So that's it. Thanks for listening. Okay. Yeah. Questions? Amar? You.
Good talk, Matei. I'm sure you saw the system that Yahoo just announced, MapReduce 2.0 next generation, or Yarn is the other code name. I was wondering if you contrasted Mesos at all with that. What do you think would be comparison between them?
Yeah, so Yahoo recently announced their next generation Hadoop design, which does try to have separate masters for each job and to eventually support non-MapReduce applications too. So, I mean, first of all, we're thrilled to see that idea actually out there. Maybe it's hard to believe for you, but when we started Mesos, we first had to convince ourselves that people would want to run something other than MapReduce. And then we had to convince academics about it, which is even harder. And now, now you have Google talking about at least 4 processing frameworks, and you have Yahoo doing this. So that's great. In terms of the design, there's not much written about the actual design details yet, so I can't really say anything about it. I think some of the things we're going for is that we really tried to have a support for diverse applications from the beginning, and I think they're starting with Hadoop, and then they're saying, well, let's see what we can tack on to support other frameworks. So we'll have to see how that works. And some of the other things we're doing, like at Twitter, we're running a lot of long-lived services on Mesos. I don't think this is their initial use case, so I'm not sure how this will work. Same thing with low-latency frameworks, such as Spark, actually, which might be a problem if the system's organized like Hadoop. Yeah, but we'll see.
Just a minor question. What was the overhead that you were seeing with Linux containers?
The overhead with Linux containers is very small, so we didn't really detect any observable overhead. Now, it might depend on the features you use, but Linux containers are, you still have one kernel running, and they're just a way to place a resource limit on a process tree, and also maybe to place it in a namespace where it can see processes or files from other containers. So it works pretty well. Yeah.
So I know Quincy went through elaborate stuff to kind of trade off between latency and locality and unfairness.
Yes, yes.
What is Mesos' stand on that?
Yeah, so actually what we've found, and this is part of the delay scheduling project, is that if you have fine-grained tasks, so short tasks, and if you have support to run multiple tasks per node, you can actually get very far with just delay scheduling. So you get very close to perfect fairness, and also you get more than 95% data locality. And I think, I don't know what's happening now in production with Quincy, and I think the Dryad workload may be different, but at least in the original Quincy paper, they were only running 1 task per node, which makes the scheduling problem a lot harder. So we'll have to see how this develops, but I think if you have more tasks per node, you can actually do pretty well with what we're doing. Yeah.
I guess the assumption about roughly evenly sized and small-sized workload might break.
Yeah, it might. Yeah, and we're looking to see exactly how much impact that has. I mean, if you have some fraction of tasks being long, but it's not 90%, you can actually still do fine with this model. So, but we have to see that based on the workload. Yeah.
Okay. Any other questions for Matei? Okay, then I guess we're going to hand it off to Justin.
Thanks.